Good morning, ladies and gentlemen. Welcome to the video notes for section 4-4 in your geometry book, covering two of the triangle congruence postulates, the side-side-side postulate and the side-angle-side postulate, or SSS and SAS. So we're going to start off by introducing the side-side-side postulate. This is a postulate that guarantees triangle congruence between a pair of triangles. What it says in words is if the three sides of a triangle are congruent to the three sides of a second triangle, then the triangles must be congruent. So what we're saying here is that in this picture, if AB is congruent to DE, which it is marked that way, AC is congruent to DF, and BC is congruent to EF, that is enough for us to state that triangle ABC is congruent to triangle DEF. So if we can show that all three sets of sides are congruent, that's enough for us to guarantee that those triangles are actually congruent. In the last section we said that you needed all 6 parts, but that's not really true. We don't need all 6 parts. We need at least 3 pieces of information. And those 3 pieces of information have to fit certain patterns. So what we're doing in this section and the next section is going through all of those acceptable patterns, acceptable sets of information that could be used to declare that 2 triangles are congruent. Now in a proof, if we use this theorem, we will abbreviate it, or this postulate, we will abbreviate it as side, 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 or SSS. So let's actually look at a proof. Here is a proof using the side, side, side congruence postulate. We start every proof the same way, that is by listing the givens. This proof has 3 givens. AB is congruent to CD. BL is congruent to CL. Notice that both of those sets of sides are already marked in the picture. And finally, L is the midpoint of line segment AD. So 2 of those givens are straight up, we're using them straight away. The third given, the midpoint given, we need to actually turn into a congruence statement. If L is the midpoint of line segment AD, we actually have already established the midpoint theorem, which says that if L is the midpoint of AD, then segment AL must be congruent to segment LD. Now, midpoint theorem is one acceptable reason there. You could also say definition of midpoint, and that would be fine with most teachers, including myself. Now, once we've got that, you'll see that in the picture we now have all 3 sets of sides in these 2 triangles marked as being congruent. That finishes this proof. It makes the triangles congruent using the side, side, side congruence postulate. This is one of those rare situations in geometry where the proofs themselves are actually easier than the non-proof questions that could come up. So let's take a look at an example of a non-proof question with the side, side, side postulate. Here we're asked to determine whether or not a pair of triangles, ABC and DEF, are congruent if A is located at 1, 1 on the coordinate plane, B is located at 0, 3, C is located at 2, 5, D is located at 1, negative 1, E is located at 2, negative 5, and F is located at 4, negative 4. Now, we could graph these, but unfortunately graphing them would not prove anything. We need to come up with a foolproof, 100% fully definite way to state whether these are congruent or not. And unfortunately for us, the most concrete way for us to do this would be by finding the side lengths of these triangles. Well, if we're talking about side length of triangles, the best way to do that on the coordinate plane is to use the distance formula or the Pythagorean theorem. If you've already graphed them, you could use the Pythagorean theorem to establish the same distances. But we're going to use the distance formula. Now, you have to think about that, though. The distance formula is found the distance between 2 points. And if we have a total of 6 points and we need to find the side lengths of these triangles, one distance formula will give us 1 side length. And each triangle has 3 side lengths. So this could take up to 6 distance formulas to complete, and it will take us at least 4. Because if we get to that 4th distance formula and we find the first side length of DEF and it is not equal to one of the 3 side lengths from ABC, that would mean these triangles cannot be congruent. So we're going to have to do at least 4 distance formulas, and we might have to do as many as 6. So if we want to find the length from A to B, that would mean that A is x1 and y1. So x1 is 1, y1 is 1. And B is x2 and y2, so 0 and 3. That would mean that the distance formula would be 0 minus 1 quantity squared plus 3 minus 1 quantity squared. So you can type that directly into your calculator, but if you don't like to use your calculator, that would be negative 1 squared plus 2 squared, which would be 1 plus 4, meaning that the distance between those two is the square root of 5 units. We would then repeat this step with points B and C, which means x1, y1, x2, y2. x1, y1, x2, y2. So we would have 2 minus 0, quantity squared, plus 5 minus 3, quantity squared. That would be 2 squared plus 2 squared, or 4 plus 4, which is the square root of 8. And your calculator should reduce that to 2 root 2. Or you should. The final side length of that triangle would be given by the distance formula using points A and C. So x1, y1, x2, y2. x1, y1, x2, y2. Meaning 2 minus 1 quantity squared plus 5 minus 1 quantity squared, which would be 1 squared plus 4 squared, or 1 plus 16, meaning the square root of 17. So these are the 3 side lengths of our first triangle, are root 5, 2 root 2, and square root of 17. So now we're going to repeat those steps with D, E, and F. We're going to start by finding the length of DE. Again, we're running a distance formula here, so x1, y1, x2, y2. And the negatives make that a little bit harder. So we have 2 minus 1, quantity squared, 2 minus 1. And then the other one is negative 5 minus negative 1. So notice how that became a plus, because negative 5 minus negative 1, that's 2 negatives that make a positive. So then that would be the square root of 1 squared plus negative 4 squared, which would be 1 plus 16, or the square root of 17. So if we look at what we've got there, that number has to match one of the side lengths from the first triangle, which it does. AC is equal to DE, which in turn would mean that line segment AC is congruent to line segment DE. See, these match. They're the same. So that's one set of sides, and that's sort of unfortunate, because if it didn't match, the problem would be over and the answer would be no. But we have to continue and do another distance formula. Say we decide to do E and F next. So EF, we've got x1, y1, x2, y2. So that would be 4 minus 2 quantity squared plus negative 4 minus negative 5 quantity squared. Again, when we subtract that negative 5, that's going to become a plus in the distance formula. So that would be 2 squared plus 1 squared, or 4 plus 1, which is the square root of 5, which does match one of our side lengths. So that's saying that AB is equal to EF, meaning that those line segments are congruent. So we need to do the final distance formula. That would be D and F. Okay, x1, y1, x2, y2. So that would be 4 minus 1 quantity squared and negative 4 minus negative 1 quantity squared. Meaning we're looking at 3 squared plus negative 3 squared, or 9 plus 9, which is the square root of 18, which is 3 root 2. Now notice that that third set of sides are are not equal. So our answer here would be no. Triangle ABC is not congruent to triangle DEF because that third set of sides is not equal. BC does not equal DF would be our reasoning. Not all three sets of sides were equal. So the answer here would be no. That does it for the first video. There'll be an additional video covering the side angle side congruence postulate. Thank you very much for your time.